In the previous video, we introduced sort of the logic for testing for one proportion using a simulation, but now we're going to use a theoretical distribution, the standard normal, or a z-distribution, and do a z-test for one proportion. To take advantage of the standard normal distribution, we have to use a standardized test statistic, and that would be z-obs, and that's the same form of every test statistic, or every t-test statistic that we've seen before. So z-obs is the statistic minus the parameter divided by the standard deviation of the statistic. And as before, this parameter comes from the null hypothesis. In our case, our statistic is going to be p hat, our sample statistic, our sample proportion. The parameter is going to be determined or denoted as pi naught, and the standard deviation of the statistic is a standard deviation of p hat. But unlike what we've seen before, this is also going to be based partly on the hypothesized value. So the standard deviation of our statistic is going to be the square root of pi naught times 1 minus pi naught all over n. So this whole thing is under the square root. So it is the square root of all of pi naught 1 minus pi naught over n. If you'll remember, our null hypothesis for the babies and helpers and hinderers example was that on average, babies are going to pick between helpers and hinderers with equal probability, or that is, it's going to be a coin toss, and we actually used a coin toss to simulate this example. So there's a 50-50 chance the babies are going to pick helpers. The alternative hypothesis is that babies are going to pick helpers more than chance, that babies actually prefer helpers to hinderers. That would be like flipping a weighted coin, where the probability of getting heads is higher than 0.5, although in this case it's the probability of babies picking helpers is higher than 0.5. And we defined pi in this case to be the true proportion of babies who prefer helpers to hinderers. Our response variable is this categorical variable, the character or the type of person that babies prefer. It has two levels, helper and hinderer. In our sample, we had a p hat of 0.875, which was the same as 14 over 16. We now have everything that we need in order to complete our z-test statistic. So z-obs is p hat minus pi naught over the standard deviation of p hat. In this case, p hat is 0.875. Pi naught comes from the null hypothesis, and we're hypothesizing that there's an equal chance of picking helpers and hinderers, so that pi naught is 0.5. The standard deviation of the statistic is going to be 0.5 times 1 minus 0.5 all over 16. So n is 16 because there were 16 babies in the sample. We use 0.5 times 1 minus 0.5 because we're hypothesizing there's a 50-50 chance that babies prefer helpers. When we work all of this out, we end up with a z-statistic of 3. We interpret a z-score, or a z-test statistic, the same way that we interpret a t-test statistic. This is saying that our sample statistic, or our sample proportion, is 3 standard errors, or 3 standard deviations greater than the hypothesized proportion. We can also think of it this way. If there really is a 50-50 chance of babies preferring or picking helpers, when given the two options between helpers and hinderers, we've observed something that is 3 standard deviations greater than that. This is a pretty big effect. And in fact, we use 3 as the cutoff for standardized values in order to determine if something is a big effect. So getting a standardized value, or a z-score of 3, tells us that this is a large difference. So what does this z-distribution look like? Well, here we have an example of the z-distribution. Now remember, the z-distribution is the standard normal distribution, so we have a whole bunch of z-scores in here. Most of our z-scores are going to be lumped around the center, which is 0. We have observed a z-score here at 3. This is our z-obs. If we think about the empirical rule, or the 68, 95, 99.7% rule, we've observed something that is 3 standard deviations greater than the hypothesized value, that is 3 standard deviations greater than 0, which is pretty unusual. This distribution is based on assuming the null hypothesis is true, for the same reason that we said if the null hypothesis is true when we interpreted our test statistic. So if we were to think about that empirical rule, or if we were to go straight to the normal distribution, we'd be able to get our p-value. So our p-value is all of this probability greater than this z-score here. That means our p-value is 0.0013. That is, if the null hypothesis is true, if babies really do pick between helpers and hinderers just by chance, or if the probability is no different than a coin toss, and the normal curve is appropriate, then we've observed something, then the probability of getting something like what we've observed or larger is 0.0013. So that is the probability of a test statistic like ours or larger if babies really have no preference between helpers and hinderers is 0.0013. In order for this to be valid, in order for this p-value and this whole test to be valid, we do have to make some conditions, and I've already alluded to one of them. The first is that we have to have a categorical response. If I don't have a categorical response, then I can't talk about proportions. I need to be able to talk about the proportion of babies who fall in the category of preferring helpers. In this case, my response is type of person. The levels are helper and hinderer. I only have one variable even being measured in this entire study, and that is what kind of person the babies look at. Do they look at the helper or do they look at the hinderer? But the helper and hinderer classification, those are the levels of the categorical variable. The categorical variable is just the type of person. So if I were to make a data table of this, I would have baby 1, 2, 3, and so on, and I would have type of person. And this first baby would probably have looked at the helper, the second baby would have looked at the helper, this third baby might have looked at the hinderer, and so on. So the levels, the actual entries in the data set, are the levels of the variable. The variable itself is how I would label the column. And in this case, I would label the column type of person. And that is a categorical response. And I have satisfied that. So now I can talk about the proportion of entries that are the helper. If I don't have a categorical response, I can't talk about proportions. The next condition or assumption that is required for the z-test for one proportion, this is one that we always have to satisfy, and that is that we have a random sample. In this case, we are hoping that we have a random sample of babies, or that we have randomization. In this case, we hope that we have a random sample of babies so that we can generalize to the greater population of babies, but we also did do some randomization of which the order in which the babies were shown the two scenarios, because every baby was shown both the helper and the hinderer character. So we need randomization, so maybe random assignment of treatments, but in this case the random order of the helper and hinderer characters, but also a random sample of babies. And that has been satisfied here. And then third, the last thing we need is that we need a enough sample. So every time that we've done a study, we've had something about the type of variables, we've had something about the randomness of the sample, and we've had something about the distribution. So for t-tests, we always have to have a normal population of the response. And that might be a normal population for all levels of the quantitative predictor or normal population for each level of the categorical predictors. Well, when we have a categorical response, we can't have a normal population because we just have a pile of responses here and a pile of responses there. So we can't really talk about normality of the population. So what we really need is to have a big enough sample so that the sampling distribution, that is the distribution of the p-hats, is approximately normal. So we need a large enough sample in order to do that. And it's about the sampling distribution, it is not about the population distribution. So it's about the distribution of p-hat. So I need a large enough sample. And this is still a distributional assumption, but it is not going to be the same as what we've seen for the t's. In this case, I get a large enough sample when n times pi naught and n times 1 minus pi naught are both greater than 15, or both at least 15. So if I have at least 15 successes, that would be n times pi naught. And if I have at least 15 failures, that would be n times 1 minus pi naught, then I can use this test. This is especially important when the true proportion, when pi naught, under the null hypothesis, is very different than 0.5. So if I have a pi naught that is close to 1 or close to 0, then I really have to be careful to check this condition. But those are the three conditions for the z-test for one proportion, and they are also the same three conditions required for a 95% or any level confidence interval for the proportion. So let's look at what that might look like. Let's find a 95% confidence interval for the proportion, and in this case for the true proportion, pi. Any confidence interval we build in this class is going to have the same form, statistic plus or minus critical value times the standard error of the statistic. In this case, our critical value is going to be a z-star. We're going to use z-star because our sampling distribution for p-hat comes from the z, or follows the z, or standard normal distribution. So our sample statistic is going to be p-hat, just like we saw for the test. Our critical value, this is going to be z-star. Now z does not have any degrees of freedom, so all I have to do is go to the jump distribution calculator and get z-star. My standard error of p-hat, so my standard error of my sample statistic, I have to be careful with this. With p-hat, when I have a hypothesized value, I'm going to use the hypothesized value to find that standard error like I did for my z-obs. When I don't have a hypothesized value, the best guess that I have is just p-hat. So my standard error in this case is going to be the square root of p-hat, 1 minus p-hat over n. Notice there is no pi naught to use because I don't have a hypothesized value when I'm doing a confidence interval. Confidence intervals and hypothesis tests are two different approaches to inference. But I do have everything that I need here. So my statistic, this is unchanged. It's 14 over 16, or it's 0.875. In my sample, I observed 87.5% of the baby's preferred helper to hinder. My z-star is 1.96. I get this by going to my normal distribution, the same way I would do with the t-distribution, and putting 0.95 probability in the middle. So I say calculate value using probabilities. And then I'm going to get a negative 1.96 here and a positive 1.96 there. For my standard error, I plug in my p-hat, so I'm going to have 0.875, 1 minus 0.875 divided by 16. I take the square root of that whole ratio, and I end up with a standard error of 0.083. I can take all these three things together, my sample statistic, my critical value, my standard error, and my 95% confidence interval for the true proportion pi is going to be 0.875 plus or minus 1.96 times 0.083. Working that out, my lower bound is 0.713 and my upper bound is 1. If you were to work this out, you would actually find that your upper bound is going to be something calculated above 1. But because we're estimating a proportion, we know that that proportion can't actually be greater than 1, so we're going to limit it. So when you're doing confidence intervals for a proportion, that lower bound for the confidence interval can never be less than 0, and the upper bound for the confidence interval can never be greater than 1, because a probability or proportion can never be less than 0 and can never be greater than 1. So we'll put a note here. The upper bound is less than or equal to 1 because pi is less than or equal to 1, because we are estimating a proportion. So I'm going to ask you to pause this video for just a moment and see if you can come up with a good interpretation for what this interval here means. I hope you came up with something like this. With 95% confidence, the true proportion of babies that prefer helpers to hinderers is contained in the interval 0.713 to 1. Now I'm going to ask you another question. Do we have strong evidence that this is different from chance? That is, do we have a big effect relative to what we would expect due to chance? In this case, yes. If babies preferred helpers the same as they would to chance, then pi equals 0.5 would be in this interval. And this whole interval does not include 0.5 and is in fact quite different than 0.5. The lower bound here is 0.713, which is 20 percentage points higher than what we would expect if babies preferred helpers due to chance. So even with just a sample of size 16, we are seeing pretty strong evidence that is a very large effect against the idea that babies are indifferent between helpers and hinderers. In the next video, we're going to look at section 10.1, which is now introducing a categorical predictor when we're looking at a categorical response.